Yeah, welcome to week 6 of Machine Learning Foundations. In this week, we'll study two important concepts in linear algebra. The first is positive definiteness. We'll look at it in the context of functions and then matrices. And then we'll move on to the most important topic which concludes this linear algebra segment, which is principal component analysis. In the first lecture today, we will understand what positive definiteness is in the context of functions. We'll define it and then make a connection to linear algebra by looking at vectors and suitable matrices. In the following lecture, we'll extend this notion to matrices to understand what it means, what one means to when he or she says a matrix is positive definite. Okay, we'll be looking at positive definite matrices, but before that, we'll motivate this using very simple quadratic functions. So consider the function two x square plus 4xy plus y square. So we want to understand what happens to this function when I differentiate. So recall at a stationary point of any function, the first derivatives vanish. In this case, it's a function of two variables, so both the partial derivatives have to vanish. So if I do f by dou x, then that is 4x plus 4y, and that has to vanish. And dou f by dou y is 4x plus 2y, and that has to vanish. Now it's easy to see that, so if I set xy to be the origin, which is 0, 0, yeah, both dou x and dou f by dou y are 0, hence 0, 0 is a stationary point of f. Now the next question is so what we have just found a point where the first derivative vanishes. So if you recall from high school, it's not clear. The important question now is, let's say question. The important question now is whether 0, 0 is a minima or maxima or neither, that neither corresponds to a saddle point. Now for this, what you have to do is, the answer to this question, check the second derivatives. Check the second derivatives at 0, 0. So all you have to do is do dou square f by dou x square, and that is very simple. You just have to differentiate this with respect to x again. So, and similarly, so this would turn out to be 4. Now dou square f by dou x dou y turns out to be 4, and dou square f by dou y square turns out to be 2. Now we'll try to understand. So before delving deeper, let's let me just make a quick remark. I mean, this answer, all of this implies f has a minima at 0, 0. We'll argue this more rigorously very soon, but let me just write a very general remark. Every quadratic function of the form ax square plus 2bxy plus cy square has a, we are claiming it's a stationary point. We're not claiming that it's minimized, has a stationary point. If you just differentiate the 4 and 2 coefficients, do not matter when I take the derivative and then check the partial, first derivatives at 0, 0. Irrespective of the coefficient here, irrespective of the coefficient in dou f by dou x and dou f by dou y, whether it's 4x plus 4y or some other coefficient, it does not matter. If I put x equals y equals 0, then I see that the derivative vanishes. So it's clear that every quadratic function has a stationary point at 0, 0. Okay. Now to the definition of positive definite. So a function f that vanishes at 0, 0, which is like saying that it's 0 at 0 and is strictly positive at other points is called positive definite. Now, if you want a very rough geometric figure, so what we have is a function like this, and this is f equals x square plus y square, and at the origin this is a minimum. Now the question that we are going to ask is what conditions on a comma b comma c ensure of x comma y equals ax square plus 2bxy plus cy square is positive definite. Okay. I mean, obviously we'll look at some necessary conditions, some obvious necessary conditions. These are not sufficient to understand if the very first condition is, yeah, there's some thing and is denoted by f greater than 0. So that just shows that f is positive definite. Yeah. Now if f is greater than 0, which is like saying f is positive definite, that is f is positive definite, then a has to be greater than 0. Now I would like you to think about this.
want to rewrite, pause, look at value of f at 1 comma 0. At 1 comma 0, what is the value of f? It's just a, and since it is positive definite, it has to be greater than 0. Now along same logic, if f is greater than 0, then c is greater than 0. I mean, again, the same y look at the value of f at 0 comma 1. Now are 1 and 2 enough to ensure f greater than 0? Again, pause and think about this. Think, if I have a function ax square plus 2bxy plus cy square with both a and c greater than 0, is it already enough to infer that f is positive definite? The answer is no. If you want an example, f of x comma y equals x square minus 10xy plus y square. So here is a function which is not positive definite. It's definitely not positive definite. Yeah, you can look at, I mean, you can easily make this function go below 0. I mean, look at again the value at 1 comma 1. It's clearly less than 0. What extra condition would allow us to infer f greater than 0? So for this, what you do is complete the square. So what you can do is you can write ax square plus 2bxy plus cy square as a into x plus b by a y square plus c minus b square by a into y square. So that b square by a into y square would get cancelled and we'll recover whatever was the original function. Now it's easy to see that, x plus b by a, so this is a positive term, okay, and this is also a positive term. Yeah, so it comes down to what is the value of a and what is the value of this. Okay, yeah, equal 0, greater equal to 0. So these two factors decide if f is greater than 0 or not. Okay, so that brings us to the third condition. So the third condition is, if f is greater than 0, then it's clear that a has to be greater than 0, and that is something we already saw. So what c minus b square by a has to be greater than 0, which is like saying that ac greater than b square. Okay. Okay, so combining three conditions, we have f of xy equals ax square plus 2bxy plus cy square is positive definite if and only if a greater than 0 and AC greater than b square. Okay. So it's this, if this and this. Okay. So that and if it's positive definite, it it's clear that at the origin it is minimized. That's clear. Just a couple of remarks. If AC equals b square, then f of this form, which is f is again this quadratic form, f of xy equals x square plus 2b xy plus by square, is positive semi-definite. We call it semi-definite if a is greater than 0 and negative semi-definite if a is less than 0. The second point is we have a saddle point at 0, 0 if AC is less than b square. Now this is so far we don't have any linear algebra really in this. Just we're trying to understand whether origin is a point where the function is minimized for a particular class of functions, which is a quadratic function. And we saw that if a is greater than 0 and if AC greater than b square, then 0, 0 is not just a stationary point, but it's also a point where the function is minimized. Now we'll see the most important connection to linear algebra. Here is where we'll bring in matrices and dot products and so on. So I'll illustrate this in again the quadratic case and then generalize. Now this can be written as xy into this matrix A, B, B, C into this. Okay. Now I'll denote V by this vector x comma y column vector, and let A denote this matrix. Then ax square plus 2bxy plus cy square is V transpose AB. And the question about positive definiteness of ax square plus 2bxy plus cy square, we'll try to relate it to this matrix here very soon. But now in general, we look at V transpose AB in a n-dimensional Euclidean space. So the way it would be is, you look at this vector x1 to xn, it's transpose. Then you have some matrix A11, A in n. This is your matrix. Okay. And then now this, I can write this as summation I equals 1 to n, summation j equals 1 to n, aij xi xj. Now let V be x1 until xn. Okay, and f of V equals a11 x1 square plus 2 times a12 x1 x2 so on ann into xn square. Now it's clear that at V equals all zeros, f of V equals 0. Place is a few examples to check if f has a minima slash maxima slash saddle at the origin. First example, imagine f of xy is just two variables, 2x square plus 4xy plus y square. Now in this case, you can infer as a saddle point at origin. Why? Since is equal to less than p square. Okay. The second example is a much simpler example. F of xy equals 2xy. I mean, for this case, if I write this in the dot product, then the matrix A turns out to be 2, 2, 2 and 1. Now, this also has a saddle at origin for the same condition. And the A matrix that makes up V transpose AV is 0, 1 and 0. And final example before I define positive definiteness in the context of a matrix. This is imagine f of x1, x2, x3 equals 2x1 square minus 2x1 x2 plus 2x2 square minus 2x2 x3 plus 2x3 square. This can be written as x1, x2, x3 into some matrix into x1, x2, x3. And that matrix turns out to be this. Okay. Now, at the origin, f has a minimum, and this is a homework. Check this. Yeah.
Okay, a recap before we end this lecture. We started looking at the notion of positive definiteness in the context of functions. And in the taking a simple quadratic function, we understood when this function is definitely positive and what are the necessary conditions. And we also figured what are conditions that are both necessary and sufficient for a function to be positive definite. We made a connection to linear algebra by using matrices and vectors to connect this notion of positive definiteness using matrices. That's the linear algebra viewpoint. In the next lecture, we'll use this connection to come up with a natural definition of positive definiteness in the context of matrices. We'll define when a real matrix is positive definite and use this notion. I mean, we'll also try to understand some properties of positive definite matrices in the next lecture.